Thanks a lot. So it's great to see everybody's interested and woken up to mixed reality in the web. And it's been a really long journey and we're really, really close. In fact, there's a lot of stuff that we can deliver right now. So, oops, let me go through here. So here's the journey that we've been through. So in 2009, we launched the first web-based AR content management system. And it was targeting the silo apps like Layer and Geneo, those sorts of things. In 2012 here, we launched our augmented web experience library, and that was back when this was called ARE. And we've been pushing the standards since then, trying to work with Kronos Group and W3C and the ISO, and really pushing this forward. And there's been a few years of horrible video pipeline issues through all the different browser platforms. And in 2016, in about September, we felt that it was stable enough that we could launch an MVP based on this. And again, I kind of tend to agree a bit about the fuck Apple thing. They really are making everybody's life really, really hard. And I'm really concerned about the amount that that does break things moving forward. But so our first goal with the MVP in September was to focus on as broad a distribution as possible, and that included iOS. So we focused on 360 and VR sort of content. But earlier this week we launched the next upgrade to our platform, and that makes it easy for anyone to create geolocated AR content in your browser, drag and drop, and that allows you to create fallback experiences for iOS. And what we're working on now is the computer vision work, and we've been doing that for a long time, and there's obviously a wealth of work that we're building on top of. But what I'd like to do is go through just a quick demo and look at mixed reality itself. So this is Milgram's mixed reality continuum. And so the scene that you're looking at, that's a standard virtual reality. So along the bottom, we have the four main modes, going from on the left-hand side, reality itself. That's the kind of meat space, just raw view that we have in the real world. And then on the far right-hand side is the fully virtual world. So this scene itself is a fully virtual world. That's 360 sort of content. There's flying cubes. Everybody loves those. Hey, Blair. And you can interact with these sorts of objects. And of course, you can put it into stereo mode, slip in a head-mounted display and just view that. That's very easy. The one that's not so commonly discussed and people find a bit confusing is augmented virtuality. And it's a bit of a horrible term anyway. But really, it's just projecting real-world sensor data into a virtual environment. And it gets pretty blurry there. But in this example, we're using the video stream and just projecting that into the scene. So the reality itself is just the raw camera stream pretty much. And then if we lay over the top of that, AR markers, now I foolishly printed that on shiny paper. But so you can overlay, it'll probably help if I get it up right, digital content onto the real world. And so the AR toolkit tracking is pretty good. It's really widely available. It works really well on mobile browsers. And so this sort of experience can be delivered right now. And if you look back into the augmented virtuality experience, really you can just put, oops, probably help if I don't get the microphone. Oh no, I turned it off, there you go. So you can just project other sensor data into the virtual scene. It doesn't have to be tied to the video texture. And actually that's one thing I would comment on, Blair. With the HoloLens and those sorts of see-through experiences, you can just turn the video stream off, and as long as you've got an alpha channel, you can really still sort of create those sort of experiences. But the key point really is that this is all just running inside a browser. So this is the full mixed reality continuum. Obviously with things like the depth sensing from Tango, those sorts of things, this just gets richer and richer. And the stuff that I'll show in a little while with the just natural feature tracking in the web, we're really at a tipping point now. This stuff works, we're stabilizing things, and it's pretty much ready to ship. Oops, let me just... So, I'd like to walk through just a brief history of computer vision to start with. So really we've been doing this for about 60 years, and if you look back, it was very primitive and took a little while to get going. There's a lot of mathematical and just general research that goes way, way, way beyond that. But this is the computer vision sort of side of it. If you look really, the AR side of it really only started in the last 20 years. So if you look, AR Toolkit was released in '99. And then it wasn't ported to the web until 2008, and that was in Flash, so it wasn't very open, but it really drove awareness and started getting YouTube videos out there of people trying these things. As per usual, more people saw the YouTube videos than the actual experience, but it started pushing things forward. 2011, Ilmari ported AR Toolkit to JavaScript, and since then it's been performing really, really well, but not very many people use it. It was really hard to get going, and the sort of things that we've done with ARJS and Jerome's doing with ARJS just makes this so much easier to get started and create this sort of content. And so what we're focused on now is the OpenCV side of this. So how does computer vision work in the browser? So this is the general pipeline that you go through, and it's pretty inefficient. That's part of the challenge. It's inefficient at the top level, but once you get into it, it's actually not too bad. So you start with the camera on the device, and you can access that through an API called getUserMedia. That's opened up camera and microphone access. From there, you pipe the stream into a video element, and then you draw that video element onto a canvas. From that canvas, you can then get that data out as pixels, and then that's what you run your vision algorithms on. And those can run in all sorts of different things, from just pure JavaScript to compute shaders like Neil was talking about before, to transpiled scriptum, that sort of thing. So let's walk through some of the key components of that pipeline. So HTML video element, there's a container, and it's for decoding and presenting video streams, and it really did change. It's surprisingly quite recent, but it really changed the web. It meant that we didn't have to have plugins, and you could present this content. But it was just a raw container where you'd have the play, pause, stop, that sort of thing. You really couldn't reach inside and do anything with it. With the 2D canvases, it gave us the ability to materialize a frame. So unfortunately, because of the way the codecs work and the HTML video element works, you don't really have a concept of a frame. It's more progressive decoding, but you can render that at any point in time to materialize that into a frame. WebGL allowed us to do that through 3D canvases, and that brought us access to the GPU. However, the 2D canvas is really GPU optimized, so you'll find that it's really fast in itself, and it does use the GPU under the hood. The really important development about WebGL, I believe, is that it gave us array buffers. And array buffers are really significant. Without them, we wouldn't be able to do any of the computer vision stuff that we're talking about. That's what allowed us to actually access the individual pixels within a frame. Before that, it was a black box container, play, stop, that sort of thing. So WebGL is great, and it's it's changed the world of 3D completely, but I think this is the real gift that it gave to the web. The ability to process streams of pixels and just raw arrays. Then in 2011, as we said, Ilmari ported AR Toolkit to JavaScript. But the really interesting thing about when that was ported was that you still couldn't access the camera. So all of the demos that were running on canned videos. So you could see it overlaying things dynamically on markers, but they had to be a pre-recorded video, which kind of defeated the purpose. So enter getUserMedia. So this really did change things. It's part of the WebRTC development. We remember the WebRTC working group, and this is really a driving force through the web at the moment. This, along with WebVR, have really kicked off like a renaissance in API development and a flood of fucking emails. But it really opens up the local device for us to be able to access that sort of content. Some people do claim that the latency is an issue, but it's really not that bad. So if you look at the latency on a camera stream in a native AR app, it's around, we're using a pixel as a reference device here, but it scales depending on the device. So 200 to 250 milliseconds from the real world event, that sort of Oculus, motion to photons sort of view of latency. So when you move something in the real world and you see that pixel move on the screen, that's about 200 to 250 milliseconds before you start doing anything, processing it, anything. The gum stream is a little bit slower, but only about 200 milliseconds. So there's a lot of things you can do to optimize that. Nyquist comes in. It's really important to get the sampling rate right. but it's definitely a workable beginning. From the Get User Media release, then we started building a whole lot of different things across the web, different people. So in 2012, we were doing putting the fast feature detection to get that working as a basis for more general natural feature tracking. And we've been working for a long time on a pure JS tracking algorithm called Tiger's Tail. And so that works really well, but it is still more fiducial at the moment. So it doesn't have this sort of hardcore fiducial corners and structures, but it's more structured. OpenCV is a really interesting option because it brings much more general computer vision work. Then from there, 2012, Tracking.js was released. So Tracking.js is really interesting. They've done some good implementations of a lot of the different standard algorithms, but the performance really isn't there. You can't generally run these in an online or real-time environment. Most of them are good for, I can recognize a face on this web page or those sorts of things. They've got some great demos and I'd recommend checking them out, and they're great for understanding how some of these algorithms work too. Then, yeah, so we moved on to ARJS. So that was released just this year, and that's brought quite a bit of performance optimization. But our focus is on transpiling OpenCV. I think a general computer vision toolkit is really required for this sort of environment. So running short on time, so I might just jump quickly into a demo. Now, I foolishly printed things on shiny paper, so I'm a bit of an idiot. But, yeah, I'm back more? No, that way, yeah, that's what I was thinking. So, yeah. So this shows natural feature tracking working in a web browser. This is a fairly shitty piece of paper and shitty image and poor lighting conditions, but it tracks pretty well. So you'll see that this is really usable now. And this is something that we'll be shipping as a library that people can use just without having to do all the transpiling and things over the next month or two. And we have a whole range of different functionality built on this. Combining this with geolocation content, so you can really make the content dynamic based on where you are as well as the things you're interacting with. And we haven't even started on the optimization yet. So with the workers, you can have rolling parallel capturing, so that can give us a lot of increase. We're adding a whole range of other filters to reduce the jitter and handle the tracking loss. And there's just a really, we haven't even started on the optimization yet, but this is going to develop really, really quickly. But the key issue that we all face, and that is why everyone's swearing at Apple, they haven't adopted WebRTC yet. They've been hiring WebRTC engineers for a couple of years now. Get User Media code is in the WebKit tree. They just haven't released it for various reasons. So there's a few strategies that we use for that. For just general vision-based experiences, you can fall back to visual search. So someone can take a photo through the web browser, you can access the file API and you can grab an image from their camera. And so you can use that to do visual search and that'll launch some content. So it's not live online, but they can get some visual content. That's great for treasure hunts and those sorts of things and looking up content about specific things. And then for location-based apps, we let our users create a simple fallback, so you can create 360 content or VR content. If you're on an iOS, it just seamlessly shows you that instead. But it's really important to remember that video see-through is not the only form of AR, and especially the users really don't care. There's some really bright white lines. I know we love having academic discussions. I've annoyed a lot of people about the definitions of these things. But in the end, the user really couldn't give a shit. They just want something that's magical, works when they tap on a link, and delivers some either utility or entertainment. And I think that's what we can really deliver now. And I think the challenge really is down to the storytelling and the art and finding something that somebody actually wants to use. Bite-sized content is fine, but they still have to want to use it. Otherwise, we just degrade down towards GeoCities over time. That's my overview of computer vision on the web. So this works on about 2 billion browsers. So that's basically the Android platform plus the desktop platform. In terms of the total mixed reality platform, that's about 3 billion devices. You had another billion in maybe for iOS. So this is a really broad platform that you can just send a link and people can click on it. So I'd encourage everybody to come and try our platform, awe.media, and you can just start creating this sort of content now, and we'll be releasing the tracking very soon. Thank you very much.
Awesome. All right, so I think we actually have time for one, perhaps two questions while we wait for the next presenters to get set up. So any questions? Oh, wow, okay.
Cool.
No, he will be out. Oh, there. Oh, yes, Alex.
Can you say something technically about what's being achieved with the transpiling? Is it straightforward?
No. It's not too bad. Like Mozilla's done a great job with Emscripten. In fact, that's one of the places where Firefox performs better. Transpiling, you know, it's a deep and technical process, but it's not. I mean, it is a form of rocket science, but it's not that bad. It's not rocket surgery. So it's something that I'd encourage people to explore. I think the more people doing this, the better. We're going to try and make this as easy to use for mainstream people as possible, but the more people doing general computer vision, and the good thing about OpenCV is it then opens up all kinds of tracking and image analysis and processing, line detection, colors, just you can more easily do those with existing algorithms that are really well proven. So.
It sounds like you guys are compiling for OpenCV's the web. Are you guys looking into using WebAssembly as well?
Yes, so we're exploring all forms, and so even back to the pure JS and the compute shaders and every form of optimization we're going through, mapping the pipelines, and often the performance issues and the performance benefits are non-intuitive, and things that you wouldn't think work really well, and things that should work really well just are dogs. Working out which of the detector-extractor combinations is really key. And even down to, certainly in the pure JS, even the type of iterator that you choose can have a massive, like 100 times impact. So, yeah. Thanks.
All right. Well, thank you very much.
Thank you.